Hi everyone, thanks for checking out the Safe Travels podcast. My name is Joey. Today I'm at the Dark Skies Festival at Death Valley National Park, and I had the opportunity to sit down with Dr. Cameron Hummels, who is an astrophysicist at Caltech. We talked all about how galaxies are formed, the importance of space exploration, and a whole lot more. Dr. Hummels, I am super excited to have you on the podcast, and I mean this in the best way possible. You are a fascinating human being with what seems like a lot of incredible stories. And first I want to focus on you and then get into astrophysics and space. But you're a lover of the national park, specifically here at Death Valley. What got you into the outdoors? And you're a runner. What got you into running?
I do indeed love the natural world, and I love getting out to the national parks as much as I can. I grew up in the Pacific Northwest outside of Portland, Oregon. So there's obviously a lot of wilderness there and a lot of people who enjoy getting out into it. I was in the Scouts growing up, and I think that really instilled a love for the great outdoors up there. So I did a lot of backpacking, a lot of hiking, a lot of running, a lot of all of these things growing up, and it's just kind of continued throughout my life. And so now accomplished a bunch of kind of long-term goals that I've had. The Pacific Crest Trail, I thru-hiked that a few years ago from Canada down to Mexico. And that started when I was a scout because I grew up on the PCT, and I remember, well, not literally, but we would camp on the Pacific Crest Trail. And at one point, I remember on a hike, we were going through Eagle Creek, and that's part of the Pacific Crest Trail, and seeing a sign that was like, this goes all the way to Canada. And it was like, you know, as a 12-year-old me, I was like, you can go all the way to Canada on this trail? And so I'd always made it like in the back of my head that I wanted to pursue this at one point, and finally did.
Wow, well, I admire that. It's funny because when I was in North Cascades, I saw a part of the PCT, and I just like walked maybe 500 feet on it and felt accomplished. So to do the whole thing is
pretty splendid.
Yeah,
it's pretty amazing.
It's hard not to fall in love if you grow up in the PNW. It's how do you not fall in love with the outdoors?
Yeah, I think it's hard. I mean, every region has its high points. You know, obviously the American Southwest, Death Valley, the Mojave, the Sonoran Deserts are incredible locations, or the Rocky Mountains. Even the East Coast has some real gems in terms of the landscape and the great outdoors that you can take advantage of. I think it's a little bit harder on the Eastern Seaboard with all of the urban development that's there to kind of find it, but it's there. And yeah, trying to experience as many of those places and as much as I can is one of the major kind of tracks and goals of my life, I think.
Right before we jumped into this podcast, you mentioned that you started your day with a 10K here in Death Valley.
Yeah.
And you have a lot of history with running in this park, including a world record of fastest time through Death Valley. What was that experience like?
It was an intense experience. There was a lot of planning that went into it, but yeah, Death Valley is my favorite park, actually. It's such a beautiful location. It's such a vast spot. Most people associate, I mean, it obviously is, you know, lowest point in the Western Hemisphere, driest location in the US, potentially hottest location in the world, at least in July, maybe not here in February. But there's so much variety and diversity here. There's probably 8 different mountain ranges in the park. The footprint of the park, it's the largest national park in the lower 48, and as such has a wide expanse in terms of the ecosystems that are here. So it's really, you can get out here and yeah, you can be in that hot desert, and it's cool for that aspect of things, but there's a lot of mountaineering that you can do around here as well, and different desert ecosystems. And so yeah, in preparation for that, it was a wild time. I spent several months, actually a couple years, after I wasn't able to do it the first year because of stomach problems following sampling some of the water sources in the park, but came back and it sure was an intense time. So yeah, as part of that, I went from the northern tip of Death Valley, Formal, there's a range up there that basically is the halt of the Death Valley Wash, and then took it all the way to the southern range, and it was around 160, 170 miles in its full extent, and tried to stay off trail for the whole of that journey, as per kind of the rules of engagement for this particular challenge, and was successful in having done so. But it was definitely, there were some foreseen and unforeseen challenges that arose along the way.
So what is the world record? What time did you set through the park?
So previously it had been just under around 7 days to make this traverse, fully self-supported, not relying on any food or water caches that you'd laid along the way, or relying on people to help you, or relying on roads or anything like that. So yeah, the first time I read about this, I was like, the length of Death Valley, it's not that long. Somebody took 7-8 days to do it. You could definitely do it in faster time. And that's part of the motivation that gave rise to me trying to do this sort of event. But all said and done, I was able to do it in about half that time. I did it in just under 4 days, covering, I don't know, something like 40-ish miles a day, which again, there are people who run 100 miles or 200 miles, maybe not 200 miles in a day, but 100-mile days. And that is by all means awesome. But it's just a different terrain out here without a trail. You're hiking through the wastes of Death Valley, or the Badwater swamps, and where your feet are sinking into the mud, and with the heat and with all the things, and you're fully self-supported, so you're carrying all your gear on your back and carrying your water, carrying your food. It adds up, and it makes it a lot slower than you'd expect.
Yeah, you alluded to it, poisoning that you had testing water sources here. I believe you got arsenic poisoning, is that correct?
I drank arsenic, but I don't think I got arsenic poisoning. The thing that gave me challenges in the year that I intended to do this, but was unable to because of stomach trouble, was I had sampled, okay, so I came here, the reason I was able to do it faster than the previous people had done it was I'm sure those people were great and motivated and prepared and all of these things. You can't do this without having a strong will and a strong ability and strong preparation. But they carried their entire water supply from the start to the end, which is a lot of water. And it's super nonlinear, right? Because if let's say you're like, well, do I have enough water? Well, maybe I'll just add a little bit more water when I start, just in case. Well, you've just added more water, but that's made you heavier, which means you're slower, which means you'll take longer. So then you're like, well, maybe I need to add more. And you can very easily snowball. And so I just wanted to do away with that entirely and not worry about carrying 90 pounds of water on my back for over a week-long expedition. I had just finished a year prior doing the Pacific Crest Trail, which was all about, at least for me, was about keeping my pack very light and being able to move fast and light. And so I tried to apply that same method here. And part of that was identifying water sources along the route so that I wouldn't have to rely on carrying everything on my back, and I could only carry perhaps a day's worth of water at a time. And so that was the bulk of the preparation and the training for this was coming out to the park and looking for, now there's not like a little tap at different locations. I mean, there are a couple of taps here at Furnace Creek Visitor Center. You can fill up your water, but I wasn't using any of that because you're not meant to use kind of support from other people. So I found, both through research and talking with the hydrologist in the park and looking at maps, and then even going so far as looking on Google Maps and finding green vegetation areas in the satellite imagery, and then going out to those places to see if there was actually surface water, even if it wasn't a documented water source. I was able to identify several different water sources along the way, roughly every 40 miles, that I was able to rely on and fill up water. But of course, with a wild water source, anything goes, right? You want to make sure to filter that water for any kind of biological contaminants that could get you sick, Giardia or Cryptosporidium, that sort of thing. But you also want to worry about heavy metal concentrations, because of course these are wild water sources. It's not like the EPA is coming out here to test the water, or the FDA is coming out to make sure that the water is safe for human consumption. And so I sent these water samples away to a water service that tests like well water sources and that sort of thing. And so that's how I know exactly what the concentrations of different minerals are in the water to ensure that I wasn't gonna die, or I would die. And so one of the things I found out from this is that a few of the water sources had higher concentrations than were legally allowed for you to drink as a potable water source, like arsenic or uranium. And in the end, after a lot of back and forth with with the Poison Control Service and calling them and being like, asking some really, I'm sure, very confusing questions for them. Like, would it be bad if I drank water that had a bunch of arsenic in it? And them saying, we cannot advise you do this, sir. And I was like, no, 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 no. And they were like, why are you asking us? And I explained this, and they're like, we cannot advise. And I was like, no, 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 no. I'm not drinking this every day for the rest of my life. I just want to drink this water for like a day, for, you know, a gallon of water in a day. Is that just level with me? Is this going to kill me or not? And them saying like, we cannot advise that you drink this water, sir. So I ended up drinking it, and it was okay. I mean, I'm not dead yet. It's been a few years. But the thing that got me sick was that I ended up drinking a bunch of water that I had filtered for biological contamination, but I still got really, really sick from it. And the conclusion from seeing a number of doctors was that I got some sort of virus that was small enough to pass through the water filter and get into my system. And so the next year when I actually went to do this, I used both chlorine dioxide drops to kill the viruses as well as a filter to remove larger scale bacteria and that sort of thing. And I haven't had problems since. So I think I'm in the clear, but it was a messy business.
Well, I wasn't exaggerating when I said that you're fascinating. I mean, what a story that is.
It certainly makes for good stories. And that's the thing, is like the experience. Sure, some of it was interesting and some of it was fun. Some of it was miserable, but that's what makes for good memories and for good stories. If you just have a uniformly like life is kind of easy or life is great all the time, you know, you need the ups and downs to make it more interesting. And maybe I fashion my own downs to make the ups better.
Well, we met because we're both at the Death Valley Dark Skies Festival.
That's right.
And you are here on behalf of Caltech. You're an astrophysicist researcher at Caltech, and your work and your research and the students you have here are all brilliant and fascinating. So super excited to dive into space with you.
Sure.
We talked about your love for the natural world, but what got you into the cosmos?
Trying to better understand the world around us and the universe around us has always been a part of me, just like growing up appreciating the natural world, whether it's the ecosystems around us or the larger cosmological ecosystem around us. And so I always had it in the back of my mind that I wanted to participate in that in some capacity, and found my way through doing an undergraduate degree in computer science, where I learned to code many years ago, and then applying that to astrophysical systems. That's been my niche. And there are other people like me, but it's been a good road. And yeah, I really enjoy, so a lot of what I work on is computer modeling of how galaxies, like our own Milky Way, how they form and how they change over the age of the universe, roughly 14 billion years as we currently understand it. And trying to take those models, which model these structures, and compare the results from these simulations against observations that we take with telescopes like the Hubble Space Telescope or the Keck ground-based telescope, or these sorts of things, to see how well we can reproduce the various different characteristics of those galaxies and thus better understand them.
So let's dive into some of that work.
Yeah.
How do galaxies form? When we're looking in our own galaxy of Milky Way, what is our current understanding of how this galaxy came to be? Well,
our galaxy, like many galaxies, like most galaxies, we think forms kind of hierarchically. It forms through mergers. The kind of morbid explanation for this is that galaxies are cannibals, that they consume other galaxies to grow. And that really seems to be accurate, both played out by the observations that we see of galaxies as well as these computer simulations. So galaxies may form in their infancy as a collapse of gravitationally bound material, perhaps seeded by dark matter, this kind of ethereal component that we don't fully understand at this point, but we can infer its properties based on the observations of galaxies that we see. So that forms like kind of a little proto-galaxy very long ago in the universe. And over time, it merges with other proto-galaxies to form larger and larger and larger structures until we have a galaxy like the one that we have today, consisting of 100 billion stars and a similar amount of gas and even more dark matter. And we can make predictions. For instance, our nearest massive galaxy to our own Milky Way is the Andromeda Galaxy. You may have seen it over the course of the last 2 nights at the wonderful skies here at the Death Valley Dark Sky Festival. And that is on a collision course with the Milky Way, and we will merge with that system in the next 4 to 5 to 8 billion years or so. And when we do that, we'll form an even larger system. So that that kind of life cycle will continue to play out into the future.
And as has been referenced here a couple times at the festival, the sun will have collapsed and consumed Earth by the time that happens, correct?
Yeah, we've got bigger fish to fry over those time scales. Our sun is kind of mid-life in its trajectory, in its life right now, it being roughly 4.5 billion years old at this point, and it's got another roughly 4.5 billion years. And so at the end of that time scale, the sun will puff up, and in doing so, it'll become what's known as a red giant star. Red because it'll be slightly cooler than it currently is, and kind of the yellow-white star that it is. And giant because it'll puff up and be spatially larger. And its outer layers may actually encompass the inner four planets, the Mercury, Venus, Earth, and Mars. So we might just get absorbed into the surface of the sun as this thing expands. But even if we don't, it's going to be problematic, because shortly after that, it's going to expel its outer layers, exposing its core, and its core will continue as a white dwarf star, a very bright but concentrated little star, and eventually fade and cool. So there won't be much left for us under these billion-year timescales, but don't sell your real estate. This is far in the future, and yeah, we've got enough homegrown problems to deal with here on Earth before we're worried too much about these kind of large-scale astronomical concerns.
Zooming out a little bit from our own galaxy, we're looking at the universe as a whole. What is the Big Bang Theory, and how does that play a role into how all these many thousands of galaxies have formed across the universe? Sure.
So the Big Bang Theory is essentially just a shorthand for how we understand the kind of dominant hypothesis we have about the universe today and its formation and its evolution over these 14 or so billion years. The idea is that the universe started in a very dense, hot state and has expanded outward and in expanding has cooled, and more structure has formed within that. So regions of higher density through gravitational forces, pull more material into those regions, and thus they have more mass, thus they have more gravitational potential, and they can draw more and more stuff in. And so this has formed things like the cosmic web of structures that you may have heard, and that's where galaxies and other kind of dense things like stars or planets have formed within these kind of filaments of this spider web looking distribution of matter. And it's continued to present day. So the Big Bang is borne out by several, it's not just somebody said one day, oh, what if this, there are a number of different pieces of evidence that point towards this as an accurate representation of how we think our universe formed and exists today. One, as I mentioned, is this expansion. So when we look at distant galaxies around the universe, they all, for the most part, appear to be moving away from us. And I can look at the galaxies there, I can look at the galaxies there, and they're both moving away from us. And of course, the naive explanation is we're at the center of the universe and everyone is like running away from us. But there's a more nuanced understanding of this, and that is that space itself is expanding over time. And so if you have two things that are right next to each other in the early universe, they might be far away from each other later on and moving away from each other because the space expanded between the two things. And what's more, from the perspective of either of those things, everything appears, you can choose any random location, everything else appears to be moving away from you yourself because you're surrounded by space, and that space is expanding, and the things that are embedded in that space around you are moving away from you. And so that's one piece of evidence, but we can look at kind of the light echo of the early universe, what's known as the cosmic microwave background. We can't see it with our eyes. It's seen, as the name suggests, it's seen with the microwave part of the electromagnetic spectrum. Special devices that are essentially like radio telescopes can see this light. And the structures that are present in there give us an idea about what the early universe looked like when the universe was much more compressed and it was emitting this light. But yeah, there are a number of different pieces of evidence that suggest that this Big Bang hypothesis is an accurate representation of what our universe started as and has evolved to today.
The furthest star and light that we can see out in the sky is 13.8 billion years away, light years away in any direction, correct? And our current view within that 13.8 billion years or light years away, are there currently galaxies forming that are being monitored, or are areas in space that have the potential to become galaxies?
Well, we can't quite see, I agree with your guess there. We can't quite see 13.8 billion light years away. It turns out that, first of all, stars don't form for the first few 100 million years. So you have to wait until matter collapses enough to be able to form stars. But the more challenging aspect is those stars, when they're so far away from us, because of course, the farther away we look, the longer it's taken the light to travel to us, and thus, essentially, we're looking back in time as we're looking farther away. In fact, as I'm talking to you right now, I'm looking back in time, and you're looking back in time when you're talking to me, because the light or the sound that we're emitting takes a little bit of time to go from me to you. So when you hear my voice entering your ear, it's, a few microseconds after when I actually said it. And when you see light scattered off my skin or my hat, it's a few nanoseconds after it actually was scattered. So essentially you're looking at the past, but it's such a short time scale that it's basically, it's infinitesimal. It happens like an instant. But that mountain, it might be a little bit longer, or down the valley, it might, because it's farther, it might be longer. But even when we look at the sun, for instance, the sun is 8 light minutes away from us. So when we're looking at the sun today, we're looking at it 8 minutes in the past, effectively. But when we look across the universe to distant galaxies, we're looking, millions or billions of light years in the past. And so we can essentially see those galaxies in their infancy, or those stars in their infancy. So the biggest challenge, I think, when trying to use this effect as a time machine, effectively, to look into the past of the universe, is that light falls off in its intensity as it travels across this distance. That's why we use telescopes, is to concentrate the light from those distant faint objects to make it brighter so that we can study it. And we can't see things at infinitely large distances because the radiation falls off so quickly. I mean, if I hold up a flashlight in your eyes, it might be blinding, but if I'm 100 meters and I shine that flashlight, that same brightness of a flashlight, it's not going to bother you at all. You might not even notice it because it's so faint. And it's the same thing with the light from distant stars and galaxies. So we'd like to be able to study all of the things at great distances, and thus, when the universe was younger, more, but it's really limited by a variety of things, one of which is the size of our telescopes to collect the light from those faint, distant objects.
So what is something that you're currently invested in research-wise? What's something that you're actively looking at Caltech?
Sure. One of the things I'm actively looking at is trying to understand why galaxies evolve the way they do. One can largely break galaxies into 2 primary categories. I mean, there's lots of subtleties, but it'd be like, if you have humans, what are 2 primary ways in which you can break down humans? You could say like old people and young people, something like that. There's of course a continuum, but you could roughly make that categorization. With galaxies, there's many different types of galaxies, but there's 2 primary kind of categories. One is spiral disk galaxies, like our Milky Way, like the Andromeda Galaxy. These are the kind of canonical way we think of a galaxy. A nice little disk with some spiral structure, looks like maybe a pinwheel or a whirlpool. And in fact, those are the names of some galaxies, the pinwheel galaxy or the whirlpool galaxy. So that's one type of galaxy. Another is what's known as an elliptical. It's less aesthetically beautiful because it looks like an ellipse. Rather than having this nice structured disk, it's much more like a single egg-like component. Now keep in mind, when you think of these things, it might have this shape or that shape, but the light that we're seeing is the result of billions of stars that are contained in that, and we're seeing their kind of aggregate starlight when we observe it. We can't make out usually the individual stars because they're so numerous and they're so distant that they smear together into kind of a haze, into kind of a diffuse component. So when I say it looks like an ellipse, it's not that it's like a big egg in space. It's a bunch of stars, like billions or trillions of stars that are on orbits that make this particular shape that looks like an ellipse. And we're just seeing all of their light together in concert. And so what my research is trying to understand is, why does a galaxy maybe why does it follow this pathway and become like a disk galaxy, or why does it become like an elliptical galaxy? And much like my earlier example of humans, with humans, we can see how humans change, that a human might start as a young person and become an old person at a later stage in its life. But it's really hard for us to follow the evolution of a single galaxy when we look up at galaxies in space, because they evolve on much longer timescales. If you think about the solar system, and the Earth makes an orbit around the sun once every year, our solar system is actually orbiting around the center of the Milky Way galaxy, but it takes like 250 million years to make an orbit. And so we haven't been looking at galaxies long enough to see them on these long timescales, to see how they change. And that's where computer simulations come into it, is that we can artificially speed up time in the computer simulation to see, does an elliptical galaxy turn into a spiral galaxy, or does a spiral galaxy turn into, or are they just intrinsically different beasts, dictated at birth, that one would take this path and one would take this path. So yeah, that's a lot of what I'm working on, is trying to understand why galaxies evolve the way they do, and through these computer simulations where we can artificially kind of speed up time and follow the evolution of these systems.
From what we know of the Milky Way, does that assist your research and your knowledge of far out galaxies? And does far out galaxies, does that provide you information for what we could learn about the Milky Way?
Sure. There are definitely differences in, as I said, the farther out galaxies we look at, we're essentially, because the light travel time is long enough, we're looking in the past and in earlier stages of their evolution, and in the universe's evolution. But yes, we can definitely learn new things, and we try and take a two-pronged attack on this, to look at the Milky Way or other galaxies nearby at the same time as looking at the same processes that may be present in galaxies that are farther away, and thus younger in their ages, their evolution. That's certainly an approach that we're trying to apply.
Like many sciences over the last century, they've evolved and changed and grown exponentially in the research and data and people contributing to that research and data. How much has computer science and supercomputers evolved and adapted what we know about space today?
Oh, a huge amount. I think this is true as a universal point, that science is accelerating in its ability to make discoveries. If you think about how things were 100 years ago or 1,000 years ago, even 20 years ago, we've made so many different developments across the field of science, from biology to quantum computing to astrophysics to what have you. And computers have really accelerated our ability to make these sorts of discoveries by simplifying some of the things that we would have had to have done by hand, or making other calculations much more portable and easy to run. So yes, and that is why I think having a set of programming skills is beneficial to anyone working in the physical sciences or the biological sciences, because it allows you to tap into this resource of computing power that you would otherwise not have access to.
Taking a closer look at galaxies now, what are the elements? You touched a little bit about dark matter and other elements that make up a galaxy, but what are the interactions that need to occur within those elements to start forming galaxies, form stars, and eventually form a planet within a galaxy?
Sure. Well, the primary force that's acting on basically anything in astrophysical scales, whether it's galaxies, whether it's the formation of stars, whether it's planets orbiting around stars, is gravity. And gravity, for the most part, is an attractive force. We think of it, it's the thing that makes it, when I drop this rock, that it falls to the ground, but really it's because the rock is being attracted towards the Earth. And this is true not, whether or not we're here on Death Valley, or we're at the North Pole, or we're on the other side, we're in China. You can still drop a rock and it's going to fall towards the Earth at the exact same acceleration rate. And this is also true of objects in space that are orbiting around things. Effectively, when something is orbiting around something else, it's falling around it. And the way you can think of this is, if I throw this rock, All right, I just threw that rock. It goes for a ways and then it falls down towards the Earth. But let's say I've got a rocket arm and I can throw that rock so fast that by the time it starts to fall down towards the Earth, the curvature of the Earth has fallen down away. So neglecting air resistance effects, as it falls towards the Earth and the Earth falls away from it, I've just thrown that into orbit and it's going to continue around the Earth and continue around the Earth, falling all the while, but it has speed that's keeping it moving relative to that fall away rate of the Earth. And of course, here it wouldn't work because of air resistance, which would slow it down and it would stop. But if there weren't an atmosphere, or if we're high enough up above the atmosphere that we can do that with a satellite or the Hubble Space Telescope or the International Space Station, that's essentially what it's doing as it's orbiting around. It's just falling. And so, sorry, I keep getting on sidetracks. But,
no, please.
But gravity is the dominant force for all astrophysical systems for the most part. And so it governs the key aspects of galaxies. Galaxies are composed, as we talked about, of stars, of gas, of dark matter, and those all have mass contributions that interact with each other gravitationally. If you take any two objects that have mass, they're attracted to each other, and that is proportional to the mass of those objects. And that's why the main gravitational force that you and I feel is towards the Earth, because it is the most massive business that's close to us. But if we were to get closer to Jupiter, which is more massive, or get closer to the sun, we would start to feel those gravitational effects as well, and we would be pulled towards those things. But this works for astrophysical systems in that if you have a big cloud of gas, say a few thousand times the mass of our sun, all of those little gas parcels in that big cloud are pulled towards each other. And the net effect is that the gas cloud, if it's massive enough, is going to start to gravitationally collapse into a smaller structure. And this happens, and we can see this. In fact, perhaps this weekend you were able to. The Orion Nebula is a beautiful instance of one of these collapsing clouds of gas that once it collapses enough, it'll fragment into little tiny chunks that those chunks start to collapse. And you can get that gas so dense, and as it condenses, it starts to heat up. It gets so dense and it gets so hot that the atoms get crammed next to each other. And when they get close enough to each other, if they get close enough to each other, you can fuse them together in a process known as nuclear fusion, where you take two hydrogen atoms and you compress them together. And well, you take four hydrogen atoms, compress them together, and you make a helium atom, the next heaviest element on the periodic table. And in that process, not only does it take hydrogen and turn it into helium, it releases energy in the form of gamma ray, in terms of radiation. And that radiation is what powers stars. It's what prevents these collapsing clouds from collapsing indefinitely down to a black hole, but it provides pressure that opposes that gravitational collapse, so it stops its collapse, it holds steady, and that is what we know as a star. It's a big cloud of gas where there's very dense in the core, it's forming heavier elements, it's releasing energy, and that energy percolates out, it gets to the surface, and then it shines. And that's why the sun shines, it's why stars shine, it's why stars glow. And that process of star formation, which we reasonably well understand, but there are still questions that we're trying to work on and better explain, that is a major part of what separates these two kinds of galaxies that we have, these disk galaxies and these elliptical galaxies. The disk galaxies have a lot of young stars that are being actively formed. The elliptical galaxies don't.
And what does the life cycle of the star look like? Do they eventually go through that same process and then that's what creates these planets? And why do planets differentiate from each other if the chemicals or the process of making up a star are similar?
Great questions. The planets we believe, and there seems to be significant evidence for this, are formed along with the stars. As the star collapses, I gave you an oversimplified version. Obviously, we can go to very, very high levels of subtlety here. As that gas cloud collapses and forms this star, there might be a little bit of net rotation to the gas cloud. Just because you take a bunch of random samplings of gas, yes, there's going to be some net collapse, but there might be a little bit of rotation. And much like a ice skater, when they have their arms out and they have a little bit of net rotation and then they pull them in and they start to spin much more rapidly, this so-called conservation of angular momentum is how it's referred to in physics. That collapsing gas cloud that has a little bit of net rotation when it's quite large, when it gets to small sizes, it speeds that up and it can develop a disk. This is known as a protostellar disk or a protoplanetary disk. And that disk of material, again, gas and dust and debris, will coalesce into individual structures known that we think that's how planets form. And that's why when we look at our solar system, all the planets are orbiting in the same plane because they formed this way and at different kind of concentric circles. And we see evidence for this in other planetary systems around other stars and other kind of nascent planetary systems around these protoplanetary disks. So it's super exciting, and it seems self-consistent in how these sorts of systems behave.
That's fascinating. You mentioned a couple answers ago, black holes. What do we
Yes.
know about black holes? Do they challenge our prior knowledge on galaxies and space?
Sure. We know some stuff about black holes. We're constantly learning more. Black holes are the idea of where this gravitational collapse kind of goes into a runaway, and nothing in the end can oppose this collapse from gravity, and everything falls down to a single point in space. Actually, a single point, not just like astrophysically a single point, but as we understand it, as small as you can make a point in space. That's where all of the mass of a black hole is, and it's at an infinite density, which is crazy to wrap your... Anytime you have infinities, you're like, oh, I can't think about infinities. But that is the idea of a black hole. And so what develops is a region around that point in space. That's called a singularity, where all the mass is. A region around that point in space where it's dark. And the reason I say that is because think about what it takes to get off of the surface of the Earth. You have to have a rocket with a lot of thrust. I can't just throw a baseball up and hope that it goes all the way out. To leave this gravitational system, you have to achieve a velocity known as the escape velocity from that system. And we can do some simple arguments about what the equation is that governs that, but essentially the escape velocity for a system is proportional to the mass of that system that's kind of holding the stuff here. The more massive the Earth is, the harder I'm going to have to throw a baseball to make it escape from this gravitational system. But it's also inversely proportional to the size of the Earth. So if I get it smaller, it also becomes harder for me to throw a baseball up and have it escape that system. And it turns out that you can increase the mass or decrease the size of something to the point where that escape velocity exceeds the speed of light. And so even if you were to throw a baseball at the speed of light, you wouldn't be able to escape that system. And so that baseball comes back down. Or if you shine a light where the light is traveling at the speed of light, that light will turn around and come back down. And then you have a black hole. And that's why it's called a black hole, is because nothing, not even light, can escape from within that gravitational field. And anything that gets too close, even light, will fall into it. And so that's kind of the basics of black holes, but we're constantly learning more. We believe that galaxies, all galaxies, and we certainly have evidence, direct evidence for this in our own galaxy, the Milky Way, that all galaxies harbor a supermassive black hole in their center. For the case of the Milky Way galaxy, that supermassive black hole is a few million times the mass of our own sun. And while we can't see the black hole specifically, we can see the region around the black hole. We can see stars that are orbiting around that black hole. And by measuring their motions, we can infer how much mass has to be concentrated in that location where the black hole is. And most recently, we've taken an image, I don't want to say of the black hole, of the region around the black hole known as the event horizon, and the accretion disk of material where stuff is actively falling onto it. That, because it's not inside of the black hole, can still glow and send light to us that we can measure. But in terms of light that's coming from within the black hole, we can't see it. And we're not predicted to ever be able to see it because of the features and the physics that I described just a moment ago.
Will the black hole eventually consume all of the Milky Way or all of the surrounding area?
No, so black holes, there's kind of a misconception about black holes that they're just huge gourmands and they're just eating everything that they can. In terms of how they interact with their surroundings, it's much like our sun would or any gravitational object. If you take the sun or you take a black hole that's the mass of the sun and you put an object in orbit, it's going to behave in the same way for the most part. Once you get really close, it breaks down, but we could replace the sun with a black hole that's the mass of the sun, and the Earth would continue to orbit in its current trajectory. We wouldn't have sunlight that's lighting our day. We'd have a little, black point up there, and there might be some other changes, but the orbit would remain the same. And so you have to get close enough to the black hole, not just close enough, but also not have a lot of relative velocity with respect to it to fall into it. And so, no, for the most part, at least in, the lifetime of our galaxy over the next several billion years, there's no concern that things are going to get so close where its gravitational field will be so dominant that it'll just fall in. Yes, it will absorb stuff over time, but it's not like the Earth is going anywhere, or even the sun. We're about 30,000 light years away from it, so we're outside of its sphere of influence for a long time.
That's so fascinating. This might be an off-the-wall question, but oftentimes on Earth we talk about climate change and anthropogenic effects from humans affecting what's going on our own planet. Do humans, with the amount of satellites and different things that we put up in space now, in monitoring stars, planets, our own Earth, do we have any effects on, residual damage to planets or stars in our own
cosmic ecosystem?
Yeah, exactly.
Oh, that's an interesting idea. We're pretty. Humanity as a species has been increasing in its power over its lifetime, over history, right? 1,000 years ago, the most damage that we could do is salt a field or something like that and prevent other plants from growing. But today we're, successful in polluting the oceans, polluting the air on a global scale. But we don't yet have the power, or haven't chosen to use what power we do, to devastate other planets or anything like this. There are proposals, and most notably people who advocate for the terraforming of other planets, that we might have that power, but it's still, planet scale power is really hard. Even if you want to do occupy Mars, according to Elon Musk and his followers, it would take such an outrageous amount of money and resources to try and terraform Mars and the entire Martian system to be more Earth-like, to melt the ice caps. It would take the GDP of the entire world for 100 to 1,000 years to have sufficient funding to be able to do this sort of thing. So it's still kind of beyond our grasp, thankfully perhaps, to have a negative impact on the larger cosmic ecosystem than just what we're doing here on Earth. Certainly, I'd say the most pressing concern, aside from things here on the surface of the Earth and the atmosphere of the Earth, is the increase in the number of satellites that are being put up. There's an effect known as the Kessler syndrome, where if you put more and more things in orbit around the Earth, eventually some of them will collide, and in their collision, when two cars run into each other, it produces a lot of shrapnel and debris. Well, all of those pieces of shrapnel and debris in orbit are then traveling at these ridiculously high speeds as they also continue their orbit. And then all of a sudden you have this kind of trash field of stuff. Even something as small as a screw, when it's traveling at hundreds of miles an hour, when it runs into a spaceship, it's going to be bad. And it could cause a kind of a compound exponential expansion in terms of the amount of debris. So that is certainly a concern in the short term of what we're doing to the very localized space environment, but we don't yet have the power to be able to influence things on larger scales than that, thankfully.
Yeah, this is more of a personal question to you. In my learnings coming here to the Dark Skies Festival, it almost makes you feel a little, in kind of a good way, insignificant. When you learn about the cosmos and everything that's happening out there. It makes you feel like, what you're doing here might not matter, might not be worth a hill of beans. That's right. Of course, we're self-aggrandizing in everything we do. You yourself are the center of your world. And so every thought that you have, and this isn't to say anything, belittle you at all. We're all doing this. We're all the center of our thoughts and the center of our world. But really, absolutely, in a global sense or in a universal sense, the work that we do or the actions that you take don't have a lot of significance on the grand scheme. Yeah, so how do you, as a researcher that's studying this constantly, that might make you feel insignificant on this planet, how do you feel motivated to keep doing that research?
Yeah, I mean, you gotta live your life somehow, and what better way than trying to better understand the nature of the world, the nature of the universe, and how the rules of the game, the rules of how that universe changes over time, than studying it and trying to help other people understand it. So I think, yeah, it's not a wealthy lifestyle, but I think at the end of the day, it's a worthwhile endeavor for our species to pursue.
And it's consumes your household. Your wife is a planetary scientist.
That's right. She's also a planetary scientist. She does astronomy, but specifically on the objects in our own solar system. Whereas, as I mentioned, I'm farther afield. I'm on larger scales like galaxies.
So do you guys ideate? Do you challenge each other in your thought processes of how things come to be or have came to be?
Absolutely. We'll talk about my research, and she's an incredibly intelligent woman and has wonderful ideas that have helped shape my direction in the terms of the research that I'm doing. And I like to think that I help her with the ideas that she posits towards me, and that I can offer some constructive criticism on ways to better deal with that. So yeah, we have some wonderful dialogues. She's great.
I certainly have a lot of questions based on some of the stuff you said. I'm sure listeners and viewers have a ton of questions on a lot of the things you have said as well. But what is that that you purvey to people about space that like gets them hooked, that they can't stop thinking about space, or they dive into their own research? What have you found with your students or just with people in general that just makes them obsessive over space?
I think it's different for each person. I think the ideas that really connect with people are the grand origins of everything. Importantly, are we the only ones out there? Is there life outside of our local Earth? Or is there life elsewhere in the solar system or beyond our solar system? And even further, is that life intelligent? Are there civilizations? I think that resonates with people of all backgrounds and all ages. And it's something that for the first time in history, we're starting to get the idea, we're starting to have the sensitivity and the ability to answer. And ultimately, if scientists are able to detect life or detect intelligent life elsewhere, that's not just an important discovery for science. That's like potentially the most important discovery in the history of the world. Like that changes philosophy, that changes religion, that changes so much about how we see ourselves in the universe. And so while I don't specifically work on the study for exoplanets and extraterrestrial intelligence, I applaud my colleagues who are working on this, and it's a very exciting time to be alive.
Absolutely. Yeah, it's fascinating hearing JPL's, NASA's Jet Propulsion Laboratory talk about some of the instruments that they're sending around Enceladus and Europa to try and see the elements that make up life on Earth as we know it here.
That's right.
When you're looking at different galaxies, though, and the formations of galaxies, you're able, through your research, to be able to tell which exoplanets are in the habitable zone of a galaxy, though, correct?
Well, it's more localized to the particular stellar system where you are. So obviously, just like in the solar system, you have various different planets at different distances away from the sun. And as such, it's like if you've got a campfire at night, if you're too close to it, it's too hot. If you're too far away, it's too cold. You want to be right in that Goldilocks zone where it's just right. And it's the same thing in the solar system. And we generally think of the Goldilocks zone where life probably can develop, the region at which you're close enough to the sun where water exists in a liquid form, because we think a lot of chemical reactions that might help speed along the development of life occur where in an aqueous environment where water is liquid. And that's more localized to different stellar systems. So when we look at galaxies as a whole, you can still have planets in their Goldilocks zone relative to their host stars in the outskirts of a galaxy or in the core of a galaxy. And there will be some second order effects, like if there's a big supermassive black hole in the core of a galaxy, there might be some intermittent radiation sources that might not be so good for the development of life. So you might not want to be right next to that thing, but you could be a lot of different locations in a galaxy and be in an environment that's stable and probably allows for the development of life, probably, according to what we think is required for life. But that that's still an open question.
Kind of a two-pronged question for you. A, what do you hope people research about space? And I think oftentimes when we talk about space, people's minds might go to, well, how does this affect me? I'm on Earth. All the events we're talking about are billions of years away. But the reality is a lot of this research that you do on space directly helps and aids inventions on Earth,
Sure.
Ideology on Earth, a lot of things. So A, we'd love for you to touch on that. But B, also, how can people just support scientists and people like yourself? You alluded to it's not the wealthiest of lifestyles, but your work is really important. So how can we allow for people like you to continue to do your research?
Sure. So to answer your second question first, a lot of support for science comes from federal funds, comes from the National Science Foundation, comes from NASA, from National Institute of Health funding science, and I think continued support of those to allow scientists to work on these important topics is necessary. Without those funding sources, 90% of the science that's being done would go away. It would just stop. Right now there's a number of proposed cuts to the National Science Foundation in the coming annual budget from the president's office of like 50 or 70%. Almost all of the science that's being done would stop in the United States. I would not have a job in 6 months. I'm not a federal employee, but I rely on funding from these grants from these federal sources, and science would just stop, and people would start doing other things, and it wouldn't be like you could turn it back on. This has been generations of people getting into this field and development. So continued support for federal funding of science, I think, is one thing. To answer your first question about why does science matter to you? Why does it matter to the person who's just trying to make ends meet? Why should we be funding these sorts of things at all? The answer I have to that is because science works in peculiar ways. Like pure research, just for the purpose of better understanding how the world works, leads to all kinds of benefits for society. And at a payout rate of like 10 to 1, the amount that you put in versus what comes out. And the example that I'll use for this is that imagine you're a rich man living 150 years ago, and you want to put money into something that's going to have a good return to you. So you look at the most dominant form, the highest tech thing 150 years ago. Steam power was the big winner. You want to dump all your money into railroads, into steam power, kind of a techno-punk kind of thing, steampunk kind of thing. How much does steam power do today? It's nothing, right? There was a person working on, there were some fidgets that we didn't really understand. Magnets. People have known about magnets for millennia, but they didn't know how they worked. Magnets are weird, right? They're still weird, right? But we much better understand them. Magnets, electricity, shocks, electrical potential. We didn't really understand these. And there was a guy, and there were many people, but most notably there was a guy, James Clerk Maxwell, in the UK, who started kind of fidgeting with these things. He was just doing pure research. He was paid to do this. And he figured out a governing theory that governs how electricity, magnetism, and optics are all tied together. And it's now what we know as electromagnetism. If we dumped all of our money on steam, we'd just be going down the wrong path. Electromagnetism has described the entire 20th and 21st centuries. It's why we have electrical circuits. It's why we have computers. It's why we have all of these things. And it's all because, not just because of him, there were many people working towards this, but if you just went with the applied thing that you thought was the best bet on return to investment, we'd just totally disregard that. And so science is all about better understanding the universe, even if it may not have a direct application to the thing that you're working on, because enough people working on enough different fields, somebody's going to make a breakthrough that's going to have implications that we could not have made predictions about before that. And that's what happens all the time. So if you cut off all these other things and try and direct it, I think it's really short-sighted, and you're going to end up, cutting off the legs of all the work you're trying to do.
I agree with you. That's beautifully said.
Thanks.
Well, I want to end on this. A couple answers ago, we talked about potentially exoplanets that might have life, and your wife obviously working in that sort of science. So what is your belief? Do you think there is life outside of Earth?
As a scientist, I have to say you have to be driven by evidence. And as of yet, we don't have evidence that there is life. That's not to say that we won't discover that in 50 years, in 10 years, next week. We are actively pursuing this. I'm hopeful that we will discover something, but we just don't know yet.
Well, Dr. Hummels, this has been an amazing conversation. Thank you for all your work, your research. And how can people learn more about Caltech and the work that your students are doing, that you're doing, and how can we direct them towards learning about that?
Sure. We have a number of different resources on the Caltech Astronomy website. We have a Caltech Astronomy YouTube channel that features 100, 200 different presentations at a public level that are given by different scientists on their, whether it's black holes or the formation of the galaxy or the evolution of the universe. And people can feel free to watch that and check out what we're doing.
Well, thank you for being at the Dark Skies Festival.
It's my pleasure.
And again, all the work that you do. This has been a blast having this conversation with you, so thank you.
Thank you very much.
Thanks for checking out this edition of the Safe Travels podcast. I really hope you enjoyed it. I didn't lie. Dr. Hummels is fascinating and brilliant, and I hope this conversation deepens your knowledge and interest into exploring space further. So if you like this type of content, it would mean a lot to me if you liked, commented, and subscribed. And until next time, safe travels.